We're going to look at chemical equilibrium. We're going to use a diagram which represents the amount of products and reactants in a system. The little purple triangles are basically the reactants, which we're going to call A, whereas the little blue dots we're going to call reactant B. And this reaction system represents a reaction A plus B is equal to C, where C is your product, which is the orange oval. The change in the concentration of the products and the reactants can be measured as a function of time. And if you look at the diagrams, you can map out the concentration of the blue and the purple particles over time. So in the T1 it drops down, T2 there's less, and in T3 there's even less particles. But on the reverse situation, the products increases. So it starts at 0 and it slowly increases 3, 5, 7 various particles. So if you look at the change in concentration over time, you'll see that our products increases and our reactants decreases. And this measure of the change in the products over the reactants, or the concentration of the products over the reactants, is called the reaction quotient. Initially the reaction quotient is 0 because the amount of products is 0, but that reaction quotient slowly increases as the reaction proceeds. And eventually it increases, so it becomes greater than 0, and eventually at equilibrium the reaction quotient is equal or almost equal to the equilibrium constant. So the equilibrium constant is basically the reaction quotient at equilibrium. We can also look at the types of species that are present. Initially, the majority species are the reactants and the minorities are the products. But as the reaction proceeds, the products become the majority species and the reactants the minority. And this is called the M&M strategy, which looks at the major and minor species that are present in a solution or a reaction system. We can also measure the rate of reaction. This can be measured either as the concentration of the products or the reactants over time. And the rate as a function of time on a graph looks very similar to the concentration over time, with one key difference. As the products increases and the reactant decreases, they reach a point in the middle, which is equilibrium. For this particular reaction, we can see that the number of products is increasing, so equilibrium has not been reached. But if we extended it further in the time series, we'd see that it would meet. This different reaction system has a different set of parameters, so a different concentration versus time graph. And you can see that not as much product is produced, the reactants decrease slower, but equilibrium is actually reached, because between T2 and T3 there's no change in the amount of product or reactant. There's change in the position of the products and the position of the reactant particles, but that change is a dynamic equilibrium, which means that the change forward for the forward reaction is the same as the change for the backward reaction. The rate for this reaction follows a similar curve, except that it reaches equilibrium much faster. And when it reaches equilibrium, the products, the reverse rate and the forward rate are equal. This one represents a faster reaction, even though the equilibrium position is actually different. In reaction system 3, we have, again, different numbers of products and reactants. In this case, it's a very slow reaction. The decrease in reactants over time is very slow, and the increase in products over time is very slow. Q is almost equal to K at equilibrium, but initially very, very slow. And this system doesn't reach equilibrium either, because you can see that there's a difference between T2 and T3. It's not at equilibrium. So our rate versus time is going to have a curve for the decrease in the reactants and an increase in the rate of products. But this also doesn't meet equilibrium. And you can see that it's a very slow rate because the slope is much lower. We can look at the equilibrium constant for this reaction. It's the concentration of the products divided by the concentration of the reactants. Now for this reaction, the amount of products is much, much less than the amount of reactants. So K is less than 1. For the previous reaction, the amount of products is also less than the amount of reactants, so K again is less than 1. And for the first reaction, if you remember, the amount of products here is greater than the reactants, so K is greater than 1. We can look at this in terms of the equilibrium position for each of these K values. So for a small K value, there's mostly reactants, which means that the equilibrium favours the reactants. For large K values, there's lots of products, so the equilibrium favours the products. For intermediate systems where the amount of reactants is roughly equivalent to the amount of products, you have K values between 0.01 and 100. These can be represented again on a graph, which looks at the concentration as a function of time. But remembering that this is just showing the equilibrium position, not how it gets there. All of these systems are at equilibrium. They just have different equilibrium positions, and that's what the K value measures.